So problem 1 from exam number 1 has a race between a tortoise and a hare. Okay, a classic story. Okay, your first question is, what is the hare's acceleration once he starts running? Well, first of all, note that this is a 1D problem, and we're told to use an x-axis for it. And because it's a 1D problem, we can use those four handy formula for 1D problems with constant acceleration, which you're told the hare has. So those are all important bits of information. So let's see what we know. We know that the hare runs, okay, for a distance of 100 meters. That's the overall race. And we know that the hare runs for a time, delta t, equals 100 seconds, starting at 900 seconds, okay, and ending at 1,000 seconds according to the stopwatch. And we'll just call this t the final velocity, the final time at the end of the hare's accelerating part of the race. The t naught is 0. Okay. We also know that the hare's initial velocity, remember these are all hare, I could put in a subscript if you want for each of them, but we don't need to, I think. So the hare's initial velocity is 0. So when I look at those formula from the first page, the handy formula, you have some options for how to solve this problem, but I happen to think the easiest one to use is the equation that reads x equals x naught plus v naught t plus 1/2 at squared. And the reason this is easy is because v naught is 0. We know delta x, which is x minus x naught, that's 100 meters. And we also know the time involved. So this one can be easily rewritten as a, the acceleration multiplied both sides by t over a. And so we have 2 delta x, remember delta x is x final minus x naught, 2 delta x over t squared. Okay, and I can plug in the values, 2 times 100 meters divided by 100 seconds squared. And you could pull out your calculator if you want, but this is pretty easy. 100 divided by 100 squared is 1 over 100. So this is just 0.0200 meters if you're worried about 3 significant figures, but the grader should accept 0.02 or just or 0.020 since we're not that worried about significant figures in this case. Now, okay, so that's part A. Part B asks for the hare's final speed. Again, we have motion with constant acceleration. If you think about the formula you've got v final at the end of some period of constant acceleration equals v naught plus at. V naught is 0 for the hare, and so you can find this easily once you have the acceleration. Just plug in that acceleration, 0.02 meters. Oh, by the way, this was meters per second squared. Okay, just plug in 0.002 meters per second squared times the time of this interval of constant acceleration, which is 100 seconds. And again, pull out of your calculator if you need to, but really all you have to do is move this decimal point over. 2.00 to 3 significant figures, meters per second, is the hare speed at the end of the interval. 2 or 2.0 would be okay for your answer. And in case you're curious, this translates to 4.5 miles per hour at the end of the race. A pretty decent speed for a human being, although we could go faster, but the hare's tired. Okay. Now, at this point, I'm going to actually check my answer. We didn't ask you to do this, but I like to do these checks as I go along. So I might notice that, if I know the velocity at the beginning and the end of the period, delta x, remember if you have a plot of velocity versus time, and if it looks something like this, the displacement is the area under this curve, or the integral of vt. So I'm just going to do a quick check and say, delta x equals 1/2 the base times the height. The base is the time, 100 seconds. The height of this triangle at the end, we just solved for, is 2 meters per second. Okay, this 2 cancels that 2, 100 meters. So this value for the final velocity, starting with v naught equals 0, over 100 seconds would lead to a displacement of 100 meters, the distance of the race. So I'm confident in my answer. So now let's do part C. Part C says, or asks, what is the hare's average speed over the entire 1,000-second race? Well, you could possibly just write down this answer if you understand that the average, okay, is just the change in position over the change in time. And for both the tortoise and the hare, they run 100 meters in 1,000 seconds. And so this is 0.100 meters per second, just like it was for the tortoise. Okay, so you didn't have to actually do this if you realize they're both the same. And again, the grader should accept 0.1 or 0.10, since we're not that worried about significant figures here. Okay, so part D. Part D asks you, at what time, relative to t equals 0, is the hare's speed equal to the tortoise's speed? Well, that's just asking you the question, at what time vt equals v hare at what time? Okay, well, we have formula for both of these. Well, actually, the velocity of the tortoise is a constant, 0.1 meters per second. I won't worry about significant figures at every step. That has to be equal to the velocity of the hare, which we know is v naught hare, which is 0, plus the acceleration of the hare. Now, the hare is running on a different time scale. I'm just going to write this as t prime, because the hare doesn't start till 900 seconds, and I'll note that t prime equals t minus 900 seconds. Okay, so to get the actual time on my stopwatch, you take the time from the start of the hare's acceleration and add 900 seconds to it. This will, I think, be more obvious in a moment. So all we have to do is solve for when this term equals that term. Oh, and by the way, we have the acceleration of the hare already. So we just want to solve the expression 0.1 meters per second equals 0.02 meters per second squared. That's the acceleration of the hare from above times t prime. Again, this is pretty easy math. T prime equals 0.1 divided by 0.02, or just 5 seconds. And you can add more zeros if you'd like, if you want 3 significant figures, but you'll see we don't need that because the actual time on the stopwatch is t prime plus 900 seconds, or 905 seconds, and that's the 3 significant figures already. Okay, so we've solved the numerical part of the problems. We're left with making plots. The first plot is a sketch of speed or velocity as a function of time, magnitude of velocity as a function of time. And so let me just draw my scales. I know on the vertical axis for E, it'll vary from 0 to the maximum speed of the hare, which is 2 meters per second. So let me just draw an axis, 1, 4, 5. 2 meters per second, 1 meter per second. Label your axes. This is velocity or speed in meters per second. I need a time axis. 3, 4, 5, 6, 7, 8, 9, 10. This is time. It'll be in seconds. Remember to label your axis. This is 1,000. The end of the race, this is 900. Where the tortoise or the hare starts running. 1, 2, 3, 4, 5. This is 500. Although it won't be so interesting. We know the tortoise is always running at 0.1 meters per second. Oh, about there. I'll just draw a horizontal line because that's a constant speed or velocity. Tortoise. The hare doesn't start running to 900, and up till then, his velocity is 0. And then it climbs linearly up to 2 meters per second. And so this is the hare's velocity as a function of time. Okay, so that's part E. Now for part F, we're asked to plot the position as a function of time for both. So let me draw similar axes. 1, 2, 3, 4, 5. 5, 6, 7, 8, 9, 10, 100. This is time in seconds. Actually, 1,000, I'm sorry. 900, so when something interesting happens, 1, 2, 3, 4, 5. This axis will be position in meters. Okay, and we know the race goes from 0 to 100 meters. Okay, and so now I can draw the formula that fit both of them. Well, the tortoise is running at constant speed, which means his position is just a times t, v times t. Okay, so it increases linearly. So this is the tortoise. The hare does nothing for the first 900 seconds, just standing around checking his phone. And his position doesn't change. And then when he does start running, his position is going to follow a formula 1/2, okay, like we have up here, 1/2 at squared. So it's going to be parabolic in t, so I want to try to draw a parabola. Okay, label that as hare. And so the graders don't take any points off. I'll just write in, okay, that the hare position is parabolic in time. Done.